This video is brought to you by mywayteaching.com.
Next is ionic or electrovalent bond. Okay, so here from the KÖssel-Lewis treatment of the formation of an ionic bond, it follows that the formation of ionic compounds would primarily depend upon the ease of formation of the positive and negative ions, okay, from the respective neutral atoms. And the second one is the arrangement of the positive and negative ions in the solid, that is the lattice of the crystalline compound. Okay, so the formation of positive ion here, the ease of the formation of the positive and negative ions from the respective neutral atoms. Okay, this point I will explain you. And it is obviously ionic compounds will be formed more easily between elements with comparatively low ionization enthalpies and elements with the comparatively high negative values of the electrons gain enthalpy. Okay, so before going to explain this point, I will explain you of this formation of the positive ions. Okay, so here, just to consider this, uh, as in the ionic or covalent bond. In this, how the formation of positive ion involves the ionization, that is removal of the electron from the neutral atom. Okay, so here, okay, this is M. Uh, this is M, okay, which is in a gaseous state, and this gives plus of G plus electron. Okay, so this is the ionization enthalpy. This is ionization enthalpy. As I'm explaining you about this one, how this is forming M plus of G, okay, plus electron. This is called what? Ionization enthalpy. Okay, next is X of G plus, this is X minus of G. This is called as electron gain enthalpy. Electron gain enthalpy. So now this gives rise to, this is like one example. Okay, so the first one is called ionization enthalpy, where it loses the electron and forming the positive ion. So here it gains the electron and forming the electron gain enthalpy. Okay, so the electron gain enthalpy is the enthalpy change when a gas phase atom in its ground state gains an electron. Okay, so this is obviously ionic bonds will be formed more easily between the elements with comparatively low ionization enthalpies. Okay, and elements with comparatively high negative value of the electron gain enthalpy. Okay, then uh, I will explain you. In ionic solids, the sum of the electron gain enthalpy and the ionization enthalpy may be positive, but still crystal structure gets stabilized due to the energy realized in the formation of the crystal lattice. Okay, so here example I will give you. So the ionization enthalpy for Na plus of gaseous, so the ionization enthalpy formation is from the from the Na of G, so that is 495.8 kilojoule per mole. Hmm. This is Na plus formation by the electron gain enthalpy. This is ionization enthalpy. Okay, this is ionization enthalpy. and I will write down here the electron gain enthalpy. Electron gain enthalpy for E minus, that is, so is equal to minus 348.7 kilojoule per mole. Okay, so while the electron gain enthalpy for the change in this is minus 3 is 1. The sum of the two, that is, how much for the sodium they have given 495.8, okay, kilojoule per mole, and that is next is electron gain enthalpy is that is electron gain enthalpy here is minus 348.7, right? So you are obtaining 147.1 kilojoule per mole. So this is the what you are getting. It is more than the compensated for by the enthalpy of lattice formation of NaCl. This is more than that of the enthalpy, than that of the enthalpy of lattice, okay, formation, lattice formation of NaCl, that is in solid. Its value is minus 788 kilojoule per mole. Okay, so therefore the energy released in the process is more than the energy absorbed. Thus the qualitative measure of the stability of an ionic compound is provided by its enthalpy of lattice formation, and not simply by achieving octet of electrons around the ionic species in a gaseous state. Okay, so this is about the ionic or electrovalent bond. Next topic is lattice enthalpy. The lattice enthalpy of an ionic solid is defined as the energy required to completely separate 1 mole of a solid ionic compound into a gaseous constituent ions. Okay, so please note down this definition. The lattice enthalpy of an ionic solid is defined as the energy required to completely separate 1 mole of a solid ionic compound into gaseous constituent ions. Okay, so I will give you example. Okay, see here the lattice enthalpy of NaCl, the lattice enthalpy of NaCl is equal to 788 kilojoule per mole. Okay, so this means that 788 kilojoule of energy is required to separate 1 mole of solid NaCl into. So this much of energy is required. This much of energy is required to separate NaCl as Na plus and of Na 1 mole of Na plus 1 mole of Na plus and 1 mole of Cl minus of G. Okay, so this is the NaCl. So this is the lattice enthalpy. Then can we move on to the next concept, that is bond parameters. In that there is a bond length. Okay, so here this is the bond length. The first parameter is bond length. Bond length is defined as the equilibrium distance between the nuclei of two bonded atoms in a molecule. Okay, so here the bond lengths, we can measure the bond lengths and by using spectroscopic, measured by spectroscope. Okay, then X-ray diffraction, X-ray diffraction. Okay, so next is in the case of the covalent bond, contribution from each atom is called the covalent radius of that atom. Here Next is the covalent radius is measured approximately as the radius of an atom's core which is in contact with the core of an adjacent atom in a bonded situation. It means the covalent radius, this is one atom. I will show in the figure here. See here, this is the figure in where you can see that this is the Ra and this is the Rb. The bond length in a covalent molecule A and B. So this is one molecule, this is one molecule, this is the center in adjacent atom, in between the adjacent atom. This is the radius of one atom, this is the radius of another atom. Okay, this is called covalent bond. The covalent radius is measured approximately as the radius of an atom's core radius of the atom core which is in contact with the core of an adjacent atom in a bonded situation. Okay, so next, this is the about the covalent radius. The van der Waals radius represents the overall size of the atom, which includes its valence shell in a non-bonded situation. Okay, the van der Waals radius. So here, how first you should note down the bond length. What do you mean by bond length? Then how we can measure the covalent radius. Next, come to the van der Waals radius represents the overall size of the atom, which includes its valence shell. Which includes its valence shell in a non-bonded situation. So here I will explain you. This is the figure where covalent and van der Waals radii in a chlorine molecule. The inner circles corresponds to the size of the chlorine atom. Okay, so this is about the figure. Okay, so next is here RVW. See here R, this one is there RVDW, and here this is the RC. Okay, so R van der Waals and covalent radii respectively. This is van der Waals. Waals radii. This is the covalent radii. Okay, so next concept is bond angle. Next is bond angle. Okay, so what do you mean by bond angle? It is defined as the angle between the orbitals containing bonding electron pairs around the central atom in a molecular complex. It is defined as the angle between the orbitals containing bonding electron. Example, see, this is this oxygen. Okay, where it is so what is the angle between them now? So you are measuring like this, 4.5 degree. Okay, so here this is the bonding angle. It gives some idea regarding the distribution of orbitals around the central atom in a molecule or complex ion, and hence it helps us in determining its shape. For example, HOH, to determine how the bond angle in water. This is H2O bond angle. Okay, bond angle in water, that is 1 out of 4. It is defined as the angle between the orbitals containing bonding electron pairs around the central atom in a molecule or the complex ion. These are the parameters, and the another one is bond enthalpy.